Today we'll look at the chain rule, which is a method for differentiating composite functions. So basically functions of functions. So if we consider this composite function of u, we can differentiate it by first differentiating the function with respect to u, and then multiplying that by the derivative of u with respect to x. So effectively chaining the derivatives together. And this can probably be seen better if we write the finite change in f with respect to x is equal to df du by du dx. And if we take the limit on both sides as delta x goes to 0, we obtain a derivative of f with respect to x is equal to the following limit. And we can split this up into two limits using the product rule for limits. And we can see that as delta x approaches 0, delta u also approaches 0. So therefore the derivative of f with respect to x, which is the same as dy dx, is equal to dy du by du dx. Let's evaluate the derivative of the following function, so we can observe it's a composite function. So we can write it as f is equal to cosine u, where u of x is equal to this expression. And now we can evaluate df du, which is minus sine u, and du dx using the power rule. And therefore df dx is the product of those two derivatives, which we are basically chaining together. So that's equal to minus sine u, where u is root x minus 2 on x, and that's multiplied by du dx, which can be simplified as follows. Let's differentiate the following function. So we can write the function as sine u, where u of x is cosine x. And now we can differentiate f with respect to u, and differentiate u with respect to x. So therefore df dx can be obtained by chaining or multiplying these derivatives together. So that will be cosine u, where u is cosine x, and that's multiplied by du dx. Let's prove the quotient rule using the product and chain rules. So we can write this as u of x by v to the negative 1. And now we can use the product rule. So f dash of x is equal to u multiplied by the derivative of v to the negative 1 with respect to x. And then plus du dx by v to the minus 1, which is 1 on v. And now we can evaluate this derivative using the chain rule as follows. So we first differentiate with respect to v, and then multiply by dv dx. And now we can write f dash of x as follows. And 1 on v can be written as v on v squared. And then v to the minus 2 is just v squared in the denominator. And we can put the negative sign over here. And therefore we get v du dx minus u dv dx on v squared. We have an explicit function where y is explicitly stated as a function of x. And here is the implicit form, where it's implied that y is a function of x. And we use the chain rule to differentiate such a function implicitly. So here is an example of the implicit form, and we aim to find the derivative of y with respect to x. So for the y terms, we differentiate those using the chain rule. So differentiate with respect to y first, and multiply that by dy dx. And for the x terms, we can just differentiate them directly. So what we end up with is 2y dy dx minus 5, which we'll put on the other side, and we divide through by 2y, and that gives the derivative of y with respect to x. Let's find the derivative of y with respect to x, and we have the implicit form as g of xy is equal to 0. So where there's y terms, we differentiate using the chain rule. So we have 3y squared by dy dx, and similarly we differentiate with respect to y first and multiply by dy dx. And for the x terms, we differentiate with respect to x directly. So 3x to the minus 1 becomes minus 3x to the minus 2, or minus 3 on x squared. And that's all equal to 0. And now we can factor out dy dx and put the remaining terms on the other side of the equation. And then dividing through by this term gives us the final result. Let's find the derivative of y with respect to x. So where we have functions of y, we differentiate using the chain rule. So cosine y and then multiply by dy dx. And for this second term, we use the product rule. So keep the first function constant, then differentiate the second function, and then differentiate the first function, so that would be dy dx, and keep the second function constant. And that's equal to 5x to the power of 4. And now we can factor out dy dx, and put the remaining terms on the other side of the equation. And then dividing through by this term gives the final derivative. Let's find the derivative of y with respect to x. So where we have functions of y, we apply the chain rule. So we differentiate with respect to y, and multiply by dy dx. And the derivative of the natural log of y with respect to x is 1 on y by dy dx. And the derivative of sine x with respect to x is cosine x. And now we can factor out dy dx, and then divide through by this term to get the derivative. Let's show the derivative of the natural log of x is 1 on x. So if we write y is equal to the natural log of x, and take e to the power of both sides, and now we can differentiate this implicitly. So for a function of y, we differentiate with respect to y, and multiply by dy dx. And on the right hand side, the derivative of x is 1. So therefore dy dx is equal to 1 on e to the y, and y is equal to the natural log of x. So therefore we obtain 1 on x. And here we've assumed that we know the derivative of the exponential function, which can take multiple representations. And we'll prove the derivative of the exponential function when we cover more advanced topics. A function f takes an input x and returns an output y, which is shown graphically using this curve, and also over here. Now to go backwards, we take the inverse of y, which is the inverse of f of x, and that gives us back x. So that's shown over here, and we can also show this graphically over here. Now for the inverse to exist, the function must be bijective, meaning that every x value maps to exactly one y value. So for example, if x3 also mapped to y1, then the inverse would not exist, because we don't know which direction to go when we take the inverse of y1. And that can be seen using something like this. Now to find the derivative of the inverse function, we just differentiate both sides. And on the right hand side, we simply have the reciprocal of dy dx. So we can use the derivative of the original function to find the derivative of the inverse function. Let's find the derivative of the inverse of this function. So using this relationship that we derived, the derivative of the inverse function with respect to y is equal to the reciprocal of the derivative of y with respect to x. So differentiating y, we can obtain the following expression. Now we're asked to evaluate the derivative of the inverse function at y equals 2. So therefore, if we solve this equation for x, we get the following expression, and we're given a condition that x is greater than -1, so we'll take the positive root. So at y equals 2, x is equal to -1 plus root 2. And if we substitute this into this expression, we can evaluate the derivative of the inverse function at y equals 2, which is equal to 1 over 2 root 2. Let's evaluate the derivative of the inverse of this function at y equals e for x greater than 5. So we use this derivative of the inverse function with respect to y is equal to the reciprocal of the derivative of y with respect to x. So therefore differentiating y with respect to x, we obtain the following result, which is equal to x minus 5. And now to evaluate the derivative of the inverse function at y equals e, we solve this equation for x. And therefore substituting y equals e, and now we're going to obtain the derivative of the inverse at y equals e by substituting this expression into here, which gives the following expression, and therefore our result is e to the power of e. Let's evaluate the derivative of the inverse of this function at y equals 1 on root 2, and the function is defined over the interval from 0 to pi on 2. So using this relationship, where the derivative of the inverse function with respect to y is equal to the reciprocal of dy dx. So what we get is 1 over cosine x. And now to evaluate this at y equals 1 on root 2, we solve this equation for x. And evaluating this at y equals 1 on root 2, so recall our special triangle. So if sine x is equal to y is equal to 1 on root 2, then the arcsine of x gives x. So for this special triangle, x is 45 degrees or pi on 4. And now we can evaluate the derivative of the inverse function at y equals 1 on root 2 by substituting this expression into here. So that gives 1 over cosine pi on 4, which is 1 on root 2, and therefore 1 on root 2 is equal to root 2. To differentiate inverse trig functions, which are of the following general form, where we have a composite inverse trig function of u of x. And here is an example, so we may have arcsine of x cubed, where u of x is x cubed. So what we do first is take the function on both sides, and on the right hand side we obtain u. And now we can use implicit differentiation to differentiate with respect to y first, and multiply by dy dx using the chain rule, and that's equal to du dx. And therefore, using some algebra, we obtain the following result. So the reciprocal of df dy multiplied by du dx. So as you can see, if u of x is equal to x, then du dx is 1. And from here, we use trig identities to obtain an expression for df dy in terms of x, which we'll do in a few examples. Let's find the derivative of the arcsine of x. So taking the sine of both sides, and using implicit differentiation, and solving for dy dx, and now we can apply our trig identity, and we can solve for cosine y. And now we can substitute for sine y, which is equal to x, and substitute that back into our derivative. And we can see that this derivative is valid, where x is between minus 1 and 1. Let's evaluate the derivative of the arc cosine of u of x. So taking the cosine of both sides, and using implicit differentiation, and solving for dy dx, and now we can apply our trig identity, and solve for sine y. And substituting for cosine y, which is equal to u, and taking the positive root, and substituting the result into our derivative, we obtain the following expression. And as we can see, this derivative is valid where u is between minus 1 and 1. Let's evaluate the derivative of the inverse tan of x squared. So if we take tan of both sides, and use implicit differentiation, we obtain sec squared y by dy dx is equal to 2x. And dividing through by sec squared y, and now we can apply our trig identity. So if we divide through by cosine squared y, we obtain the following expression. And now if we substitute for tan y, we obtain x squared squared. And substituting for sec squared y, we obtain our final result. Let's differentiate the arc cosec of x. So if we take the cosec of both sides, and use implicit differentiation, and solve for dy dx, and now we can apply our trig identity, and if we divide through by sine squared y, to get an expression for cosec y, and now we can subtract 1 from both sides, and take the square root of both sides. And recognizing that cosec y is equal to x, we can substitute into this derivative. And we'll take the positive root. Now if you plot the arc cosec of x, you'll recognize that the slope is always negative. So therefore, we'll take the absolute value of x, and x must be greater than 1 for this square root to be valid, and therefore this derivative to be valid. Let's differentiate arcsec x. So taking sec of both sides, and using implicit differentiation, and solving for dy dx, and now we can apply our trig identity. And to obtain an expression for sec y, we divide by cosine squared y, and subtracting 1 from both sides, and taking the square root of both sides, we get an expression for tan y. And recognizing that sec y is equal to x, so I have x squared here, and substituting the positive root back into our derivative, so we have x by the square root of x squared minus 1. And if you plot the arcsec of x, it's valid for both positive and negative x values, and the slope is always positive. So therefore we take the absolute value of x to keep the slope positive, and to satisfy the square root, the absolute value of x must be greater than 1, where x can be both positive and negative. Let's find the derivative of the arc cotangent of x. So taking the cotangent of both sides, and differentiating implicitly with respect to x, we get minus cosec squared y dy dx is equal to 1. So therefore dy dx is equal to minus 1 over cosec squared y. And we can use the trig identity of cosine squared y plus sine squared y is equal to 1, and dividing through by sine squared y gives cotangent squared y plus 1 is equal to cosec squared y. And we can see that cotangent squared y is equal to x squared, so therefore this expression becomes minus 1 over 1 plus x squared. Here is a summary that can help you remember the derivatives of inverse trig functions. So you don't want to be applying implicit differentiation all the time and using trig identities to obtain these expressions. So in general, the derivative of an inverse trig function is basically a function of u multiplied by du dx. So you can substitute u directly into the expression. And the derivative of arcsine and cosine differ only by a negative sign. And similarly, the derivative of arcsec and arccosec also differ by a negative sign. And so do the derivatives of arctan and arccot. So study these to learn the patterns, and you can apply them directly to practice problems without having to rederive them. Let's differentiate the following function. So this is a quotient of two functions, and we'll thereby apply the quotient rule. So we keep the lower function constant, and differentiate the higher function, and then minus the upper function by the derivative of the lower function. So this is a composite function, so we'll use the chain rule. So it'll be e to the u, where u is equal to root x minus 3, and then differentiate e with respect to u. So that would give you e to the u, and then multiply that by du dx, which is 1/2 x to the minus a half, or 1 on 2 root x. And that's all divided by the lower function squared. Let's differentiate the following composite function using the chain rule. So we have y is equal to sine u, where u is equal to cosine v, and v equals sine x. And therefore by the chain rule, dy dx is equal to dy du by du dv by dv dx. So dy du is cosine u, du dv is minus sine v, and dv dx is cosine x, and you can substitute for u and v to get the final result in terms of x. Let's differentiate y with respect to t. So in this case, y is a composite function of x, and x is a function of t. So we can use the chain rule and differentiate y with respect to x. So that can be done using the quotient rule. So we have low d high minus high d low over the square of the lower function. And we differentiate x with respect to t. So that gives 2t on 2, which is t. And therefore dy dt is the product of these two derivatives using the chain rule. So what we obtain is the following result. And now you can substitute for x to write the derivative in terms of t. Let's differentiate the following function. So we can see that it's a composite function, and we can thereby write y is equal to e to the u, and u is another composite function. So we can write u is equal to v squared, and v is equal to the rational polynomial in the brackets. And now we can differentiate y with respect to u, and differentiate u with respect to v. And to differentiate v with respect to x, we can apply the quotient rule. So we have low d high minus high d low. And that's divided by low squared. And now to obtain a derivative of y with respect to x, we simply chain these derivatives together. And once you substitute for these derivatives, you can back substitute for u and v to get the derivative in terms of x. Let's find the derivative of y with respect to x. And because we have functions of y, we can use implicit differentiation. So for the first term, we have e to the natural log of y, which is simply y. And differentiating this term with respect to x, we get dy dx. And to differentiate tan y, we can use the chain rule. So differentiate with respect to y first, and multiply by dy dx. And on the right hand side, we can differentiate with respect to x directly. So that'll be 4x to the minus 2. So we get a plus 8 on x cubed. And I'll leave it for you to do the algebra to obtain the expression for dy dx. Let's obtain a derivative of y with respect to x, And because we have functions of y, we can use implicit differentiation on those terms. So cosine x squared is a composite function, so we can write it as cosine u, where u is equal to x squared. And now we can differentiate with respect to u, so that will be minus sine u, where u is equal to x squared, and then multiply this by du dx. And we can also differentiate the second term using the chain rule. So differentiating sine u with respect to u, we obtain cosine u, and then differentiating u with respect to x, we can use implicit differentiation. And on the right hand side we have 4y to the minus 1. So we first differentiate with respect to y, that will be minus 4y to the minus 2, and multiply by dy dx. And differentiating the second term with respect to x, we obtain minus 3. And now you can group the dy dx terms together and do a bit of algebra to obtain this derivative. Let's differentiate the following function implicitly. So we can set the function f is equal to sine u, where u is equal to x cubed by y to the 4. And therefore df dx is equal to df du, so that will be cosine u, and u is equal to x cubed by y to the 4, and that's multiplied by du dx. So using the product rule, we have 3x squared y to the 4, and then plus x cubed by 4y cubed dy dx. And now we can set all of this equal to the derivative on the right hand side. So that will be 20x cubed, and then we can solve for dy dx and get the final result. Let's evaluate the derivative of the inverse function of y. So recall the following relationship between the derivative of the inverse function with respect to y and the derivative of y with respect to x. So we can differentiate y using the chain rule. So y equals e to the u, where u is equal to 1 on x, or x to the minus 1. So therefore dy to u is e to the u, and du dx is minus x to the minus 2, which gives the following result. And now we need to evaluate the derivative at y equals e. So therefore we can solve this equation for x by taking the natural log of both sides and taking the reciprocal of both sides. And at y equals e, x equals 1 over the natural log of e, which is 1 on 1. And now to evaluate the derivative of the inverse function at y equals e, we can substitute x equals 1 into this expression. So what we get is minus 1 squared over e to the 1. Let's find the derivative of the inverse tan of x on 2. So we can write this as y is equal to the arctan of u, where u is equal to x on 2. And therefore we can apply the derivative of the inverse tan that we derived earlier directly. So that will be 1 over 1 plus u squared, and that's multiplied by du dx. Let's find the derivative of the arcsine of e to the x. So we can write this as the arcsine of u, where u is equal to e to the x. And now we can apply the derivative of the inverse trig function that we've derived earlier. So for arcsine u, that will be 1 over the square root of 1 minus u squared. That will be 1 minus e to the x squared. And we multiply this by du dx, which gives e to the x in the numerator. Let's find the derivative of the arc cosec of x cubed. So we can write this as the arc cosec of a function u, where u is equal to x cubed. And now we can directly apply the derivatives of the inverse trig functions we've derived earlier. So for the arc cosec of u, that's minus 1 over the absolute value of u by the square root of u squared minus 1. And we need to multiply by du dx. So that will be 3x squared in the numerator. And you can think about the values of x for which this derivative is valid. Let's find the derivative of the arcsec of the natural log of x. So we can write this as the arcsec of u, where u is equal to the natural log of x. And now using the derivatives of the inverse trig functions we've derived earlier, the derivative of the arcsec of u is 1 over the absolute value of u by the square root of u squared minus 1. And we need to multiply by du dx, so that will be multiplied by 1 on x. So far we've looked at the first derivative of a function, and if we differentiate again, we obtain a second derivative. So that's the same thing as taking a derivative of the first derivative, which is also the same as taking the second derivative of the original function with respect to x. And we can also write another notation, so f dash dash of x, to represent the second derivative. And similarly, the third derivative can be written in the same way using these different notations. And in general, if we keep differentiating our function, assuming the derivatives exist, we can write the following notations for the derivative. So the nth derivative of y with respect to x is equal to fn of x, where we differentiate the function n times. Let's find the second derivative of this composite function. So we can write y is equal to sine u, where u is equal to 2 on x, or 2x to the negative 1. So therefore, the first derivative of y with respect to x is cosine u by du dx. And now we can use the product rule to obtain a second derivative. So keeping the first function constant, and differentiating the second function, and then differentiating the first function using the chain rule, we get minus sine u by du dx. In a similar way, we obtain the first derivative. And keeping the second function constant, that's multiplied by minus 2 on x squared. And I'll leave it for you to do some algebra to simplify this derivative. Let's obtain the second derivative of y with respect to x using this implicit form. So using the chain rule, we have 3y squared dy dx plus 4 dy dx minus 8x, and the derivative of 3x to the minus 1 is minus 3x to the minus 2. And now we can use some algebra to obtain the first derivative. And now to obtain a second derivative, we'll apply the quotient rule. So we keep the lower function constant, and differentiate the upper function, and then minus the upper function kept constant, by the derivative of the lower function, which we can obtain using implicit differentiation. And all this is divided by the square of the lower function. And now I'll leave it for you to substitute for the first derivative, and do some algebra to simplify this second derivative. Let's obtain a second derivative of y with respect to x. So using implicit differentiation, we can see that this is sine u, where u is equal to y squared. So using the chain rule, we differentiate with respect to u, and then multiply by du dx. That'll be 2y dy dx. And that's equal to 3. And now we can write the first derivative. And using the quotient rule, we can obtain a second derivative. So we keep the lower function constant, and differentiate the upper function, and then minus high by the derivative of the lower function. So we obtain that using the product rule. So keeping the first function constant, and differentiating the second function, we obtain minus sine y squared by 2y dy dx. And then differentiating the first function, and multiply by the second function kept constant. And all of this is divided by the square of the lower function. And substitute for dy dx to obtain your expression for the second derivative. We can use the rules for logarithms to evaluate the derivatives of certain functions. So for example, we have a composite log base a of the function u of x. So if we take a to the power of both sides, and now take the natural log of both sides, so we get y by the natural log of a is equal to the natural log of u, and dividing through by the natural log of a. And now we can differentiate this using the chain rule. So dy dx is dy du by du dx. So 1 on the natural log of a is a constant, and the derivative of the natural log of u is 1 on u, and we multiply this by du dx to get our final derivative. So if u is equal to x, that's a special case where du dx is equal to 1. We can also use the rules for logarithms, where we have exponential functions. So if we take the natural log of both sides, and use the rules for logarithms, we obtain u by the natural log of a. And now take e to the power of both sides, we obtain the following result. And now we can differentiate y with respect to x using the chain rule. So first we differentiate with respect to u, and multiply by du dx. And now we can see that this term is equal to y, and y is equal to a to the power of u. So we can write the derivative as a to the power of u by the natural log of a by du dx. And for the special case where u is equal to x, du dx is equal to 1. Another application of logarithmic differentiation is where we have the quotient of two functions, and these quotients are quite complicated. So what we can do is take the natural log of both sides, so that gives us the natural log of u minus the natural log of v. And in separating these functions, we can use implicit differentiation. So applying implicit differentiation, we use the chain rule. So that gives 1 on f by df dx, and that's equal to 1 on u by du dx, and minus 1 on v dv dx. And then we can multiply through by f and substitute these expressions and do a bit of algebra to obtain our final derivative. And we'll see how convenient this is in an example problem. Let's differentiate the following composite logarithmic function. So we can write this as y is equal to log base 3 of u, where u is equal to x cubed plus 2x. And we can write an expression for the derivative of y with respect to x, and we've derived an expression earlier. So that will be 1 over u by the natural log of the base. And that's multiplied by du dx, which is 3x squared plus 2, which we can put in a numerator. Let's differentiate the following function. So we're going to apply the product rule and keeping the first function constant, multiply by the derivative of the second function. That's equal to the natural log of the base by 3 to the x. And we've derived an expression for the derivative of exponential functions earlier. And now we add the derivative of the first function and multiply this by the second function. And you can do some algebra to simplify this expression. Let's differentiate this function, which is a quotient of two functions. So taking a natural log of both sides, we can apply the rules for logarithms to separate these functions. And we can further simplify this last term, as the natural log is the inverse of the exponential function. And now differentiating both sides with respect to x, we can apply the chain rule on the left hand side, and on the right hand side the derivatives are quite straightforward to evaluate. And now we can multiply through by f and substitute this expression. And I encourage you to simplify this and evaluate the derivative using the quotient rule and compare the result. Let's evaluate the following derivative of a composite exponential function. So we can write y is equal to 4 to the u, where u is equal to sine x. And to obtain dy dx, we can use the expression we derived earlier. So that would be 4 to the power of u, which is sine x, by the natural log of the base, and that's multiplied by du dx, which is cosine x.